go right ahead and put a plus 3 at the back because I'm everyone you know. However, if there is a vertical translation already on the equation, and you get another vertical stretch or a vertical stretch on that, you will get it wrong every time because it's just one of those people who forget. So always just put it with your y first and move it over. I know in this case it wouldn't matter, but there are going to be cases where it does and you will get it wrong every time. Okay? Remember, I have my story, I tell people this, and then they come to the diploma and they're like, crap, I did it wrong, and you told me I would. Don't be those people. Be like, yes, man, high five, I did it right. Okay, so we get y minus 3 equals square root, and that x is going to be replaced with x plus 4, so it's underneath. And then I'm going to add the 3 over, so y equals square root x plus 4 plus 3. These should be easy questions, because they just have horizontal and vertical translation. So the answer, 2. The graph of y equals f of x has transformed to the graph of y equals x of x plus 3 minus 2, which is the following statement which describes the transformation. So the graph has been translated. This is going to be vertical translation down, 3 down, and 3 left, and horizontal, wow. Horizontal translation 3 left, and a vertical translation 2 down. Now remember what I told you to do? I always just multiply y first, so it's going to be y plus 2 equals f of x plus 3. And then if you split the variable, you always do the opposite. So that's what I just do. I always move it with the variable first, and then I know it's over here. So 3 left and 2 down. This is 2 units left, so that's not good. This is 3 units to the right, so that's not good. And then just mapping. So if it's 3 left, it's going to be x minus 3. And if it's 2 down, it's going to be y minus 2. So numeric response. As a result of the transformation of the graph y equals x cubed into the graph of y minus 4 x minus 3 cubed, the point 327 becomes 6 of y. What's the value of y? We're changing a point. Whenever we change a point, we use mapping, remember? So xy is going to become x plus 3, so you need 3 to the right, and y plus 4 is going 4 up. Because when I with the variable, you move to the opposite, and then I can plug the points in. So 327, 3 plus 327 plus 4, 3 points becomes 6 and 31. 31. You fill in the numeric response boxes, you fill left to right, and only as many boxes as you need, so it would be 31. Okay? You fill in the way you read. The partial graph of y equals f of x is shown. The range of the function f of x is greater than or equal to negative 11. If the graph of the function is moved, transformed to g of x, then the range of the function will be. So I don't actually care about horizontal translation on my range, because it's just going to move the graph this way or this way, and the domain on this is xdr. What I do care is how it moves it, up or down. So this is going to move it, and I'm going to move it over here. G of x plus 3 equals f of x plus 1. So if the plus 3 is moving it down 3, if I move it down 3, you move it to negative 14, and it's still going to be greater. Now keep in mind, once you put in reflections, if there was an actual reflection on the x-axis, that would pop it down, it would be less. So the more transformations we add onto this, the harder the question. Okay? Give yourself a mark on 4 at the top, and I'll take it and I'll hand it back to 4 at the same time. And then open your notebook. Stretches of a function. A stretch is a transformation that changes the size and the shape of the graph. The original and the new graph are not congruent. There are 2 types of stretches. There's vertical and horizontal. Last year you dealt with vertical, but you didn't deal with horizontal, and you dealt with them on such a small scale as compared to what we do now. Vertical stretches are the form y equals a f of x, or you could have this, you could divide that a back over here and have 1 over a y equals f of x. can have the A in front or have it with the Y, and I always like having everything with the Y because it flips. So this says vertical stretch, so where A stretches the graph vertically by a factor of A. If it's with the Y, you always flip your stretch. So instead of this being 1 over A, it's actually a vertical stretch by a factor of A over 1, which is just A. You always flip it when you flip the variable. So this is going to be, we would say this vertical stretch by a factor of. Now this here, I will write this from now on as EAFO, for laziness. Okay? The vertical stretch by a factor of, and this would be A, because it would be 1 over A, so it would be A, about the x-axis. Because it's with the y, it's about the x-axis, just like it's when it's with the y, it's a reflection in the x-axis, same thing. When it's with the y, it's about the x-axis, or a reflection in the x-axis. Your point, what you do when you have a stretch, so when you have a reflection, you multiply the variable by that -1, correct? When you have a stretch, you're going to multiply the variable by that. So it's a vertical stretch by a factor of A above the x-axis, so x is going to stay the same, and A is going to become AY, A times Y. The points on the x-axis are invariant. Why are the points on the x-axis not changing? What's your y value when the point is on the x-axis? 0. And when you multiply anything by 0, what do you still get? 0. So stretches, vertical stretches multiplied by that value, right? But if your value is 0 and you times it by something, it's going to stay the same. So that's why the points on the x-axis are invariant when you have vertical stretches, because vertical stretch only multiplies the y value, your x value. If A has a negative sign, this is huge. If A has a negative sign in front of it, that is a reflection in the x-axis. You will never say vertically stretched by a factor of -A. The negative doesn't stretch it any more or any less. The negative doesn't do any of that. The negative reflects. Okay? So you're never going to see negative. If in your answer on the diploma you have vertical stretch by a factor of -3 or -2 or anything like that, instantly cross that question out. And that answer out. It can't be that answer. Because your stretches are always positive. That negative doesn't do anything to stretch it. That negative reflects it. We just proved that on Thursday. Right? So we never ever write negative. So describe the transformations that occurred if the original graph of y equals -4 f of x plus y equals f of x. So I'm going to move it over with the y, because that's what I do. How do I move it over? I divide by -4. So y divided by -4, I can just rewrite it as -1 over 4 y equals f of x. And that should look like this. -1 over 4 y. I always move everything with the variable because then you always do the opposite. When it's with the variable, you do the opposite. So when your translations are with the variable, it's the opposite. If it's positive, you go down. If it was negative, you go left or right. Correct? So same thing here. If this is a quarter, you're actually vertically stretching it by a factor of 4 over 1. Okay? We will maybe like, well, why wouldn't I just leave it over there? Because your x is always with the variable. So your horizontal stretch will always flip. So this makes your vertical stretch always flip too. If you only flip some and you don't flip others, then you get it all mixed up. This way I just do consistently. You're always flipping. You're always changing the sign. Okay? Always, always, always. So this is your, whenever it's with the y, it's a vertical stretch. So we also start with stretches first, right? SRT. It's a vertical stretch by a factor of a quarter, 4, negative a quarter, -4. What do you think? You ever say negative for stretches? No, so those are out. And if it's with the y, you flip it. So you'd either flip the sign if it was a translation, or you flip the actual number if it's a stretch. So if this is 1 over 4, it's actually a stretch by 4 over 1, which is just 4. So it's vertical stretch by a factor of 4 about the x-axis. What does that negative give us? A reflection. And because it's with the y, it's a reflection in the what? What's it a reflection in? The x-axis. Is it just a y for a stretch or a reflection is in the x-axis? Did you say reflection in the x-axis? Did you say reflection about the x-axis? They mean the same thing. But in or about. There are no transformations because you don't have y plus anything and you don't have x plus anything or x minus anything or y plus anything, right? Given the graph of y equals f of x, use the table of values to sketch y equals 2 f of x. Okay? So, first off, I'm going to move that 2 over by dividing it. So y equals 2 f of x. I'm going to divide both sides by 2. And I'm going to get 1 half y equals f of x. So I have a vertical stretch. I know I didn't ask you this, but it's very practice more than one enough. Vertical stretch by a factor of what? 2. 2 of what? About the x-axis. Now, if it's a vertical stretch, you multiply by that number, right? If it's with the y, it affects the y coordinate. If it's with the x variable, it affects the x coordinate. Okay? So whenever we're changing points, this is changing points here. Whenever we change points, we use mapping. Whenever we change points, we use mapping. Whenever we move a graph, we're changing points, so we use mapping. Okay? Mapping, 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 mapping. So the original coordinate would be x, y. My new coordinate would be x, comma, 2y. Because I'm going to multiply every y by 2, because I'm stretching it by 2, right? Stretching it by 2 is multiplying by 2. So my x values are staying the same, and my y values are stretching by 2. So these babies are staying where they are. They are the invariant points. Why are they invariant? Because their y values are 0, and when I multiply 0 by 2, they stay at 0, and my x is nothing happens, right? Now, they're only invariant points if all you have is a vertical stretch, right? If we add a horizontal stretch on it, then it would still be okay, but if we add a vertical translation on it, it's going to move those off of that x-intercept, right? So you have to watch. Now, this coordinate here is at -1 and 2. Sorry, -1 and 2. So it's become -1 and 2 times 2. So it's actually going to be at -1 and 4. This one is at 0 and 1, 2, 3, 4, 5. Once you have mapping, you literally just run it. So x is 0, 2, y is 5. So 3 is 0 and 10. And it's measured up. That's on the graph. And it's vertically stretched, right? Because you're stretching it vertically like this. About the x-axis, because if you have some below, you'll see it's, say you had -2, it would have went to -4, right? So we would be stretching it about the x-axis. That's how you say x-axis. And it's vertically stretching it. You're vertically stretching it. Right? Have you done that? So graph y equals x squared. We're going to do that. Graph y equals x squared. If you don't know what the points are, you can plug them in C, or you can go to your table of values and put them off. But when x is 0, y is 0, because 0 squared is 0. 0, 0. When x is 1, 1 squared is 1. When x is -1, -1 squared is 1. So it's at -1. And it's at 2 and 4. -2. And 3 and 9. What's the domain of that graph? Don't quite right. It's going to be XER. Because if I ask you, can you find x equals 0? Yes, x equals 1, 2, 3. You find 4, 5, and all the decimals in between, right? Maybe 1, maybe 2, maybe 3, maybe 4, and all the decimals in between. So just an aside, we didn't ask you this, so I want you to write it. Domain is x such that x is now in real. Now that's set notation. I can also ask it for us an interval notation. Interval notation, I find actually once you learn it, is easier than set notation. It's just like basically representing the number line. So if I represented XER in the number line, and this is x value, it would be every single value. This is 0, for example. The whole number line would be covered because every x value I can find one, correct? What does this arrow represent? Negative. That's an I rhyme for infinity. Infinity, yeah, negative infinity, guys. And then what's this one? Infinity. You can put positive infinity and that makes it hard to say. Whatever you want. Yeah. And you're just going to represent that in interval notation. Can you ever equal infinity? Infinity isn't a number, it's a concept, right? So you can't equal it, so you're going to do a round bracket. If you could equal something, you would do a square bracket, okay? But we can't equal infinity. So we can go domain is going to be from negative infinity, going from left to right, comma, all the way to positive infinity. Round bracket. And do round brackets because that means not equal to. Now some people get this confused with a coordinate. That's not a coordinate, that is your domain. Your domain is every x value from negative infinity to positive infinity, right? Which I feel like makes more sense than x and L than the real number to most people, because they can actually picture it today. Now if I did range for this graph, my range would be, what's my lowest y value? 0 or higher, right? 0 or higher means y is greater than or equal to 0. If equal to 0, it actually is 0, right? So we go y such that, I'll put this little line in means such that, we don't straight that just to save time. It's y value such that y is greater than or equal to 0, and then you put behind it y(er). Now the reason why you do that, everything here means the setup. Everything on that is not just like there for looks, it means something. The little brackets mean a setup, y values, such that y is greater than or equal to 0. Now all those values of y that are greater than or equal to 0 are real numbers. So that means decimals I can count, right? I can count whole numbers, I can count integers, all that stuff, because those are all those real numbers. Now, if I do that on the number line, I would go to 0. I would have a closed dot because it's equal to it. And I would have greater than it, correct? Yeah? You guys told me this arrow is positive infinity, so it's still positive infinity. Now I want to represent that shaded region in an interval, right? So I start the left from 0, but this time I have a square bracket instead of a round bracket because it's equal to that 0. When you close and fill in the dot, when you fill in the dot, that means equal to, right? So that's equal to 0, you have the square bracket. Comma infinity, round bracket. Infinity will always be round. You can't equal infinity. Right? With interval notation, so many times does it come up like that, and in calculus we use equal notation all the time. We don't really use set notation very often. So I just wanted to go over those just so you have a little domain range. Not this question asks you anything about domain range, but just so you kind of have a little fun on the weekend. Because you were taught this last year, how to very, very, very tiny. Very tiny. Okay. So graph y equals x squared, then replace y with 3y. So this y is going to become 3y. We're going to get 3y equals x squared. and graph it on the same axis. So we're changing a graph. We're changing a graph, we need to do mapping notation, correct? Whenever you change points or graphs, now it should just be part of the being, right? So my original point is x, y. What is this 3? What kind of stretch? Vertical stretch. Vertical stretch by a factor of what? It's with the y, so we flip it. So it's a vertical stretch by a factor of, this is 3 over what? Not over anything. It's 3 over 1. Every number can be written over 1. So it's a vertical stretch by a factor of a third. So we're going to get x comma a third y. So every x stays the same, and every y is going to be multiplied by 3, or multiplied by a third. Multiplying by a third is divided by 3, right? So it's going to say the same. It's invariant. Has 0. If I plug in 0, 0, I would get 0, 0. If I plug in negative, oh, that was it. If I plug in negative 1, 1, I'm going to get negative 1 and then 1/3 times 1, which is actually negative 1 and a third. So it's going to be real, yes. If I plug in 1, I'm going to get a third as well. If I plug in negative 2 and 4, I'm going to get negative 2 and a third of 4. Which is negative 2 times 4/3. Or negative 2 times 4/3. 4/3 is 1/3. So you're going to go negative 2 and 1/3. And you're going to go positive 2 and 1/3. So we're going to do that. So actually, when your stretch is a fraction between 0 and 1, the graph actually gets wider. And if your stretch is a value greater than 1, your graph actually gets wider. Because it's going to pull it up faster, right? They used to ask for it widens by a factor of a narrows by a factor of a. You guys try to example. So draw the square root of x. We get 0, 0. Then you fill in a 1. Square root of 1 is 1. 1, 1. Fill in a 4. So I'm not going to fill in anything other than that, because I want to get an actual number. If I fill in a 3, I'm going to get this. So I'm going to fill in 4. Square root of 4 is 2, so that's 4 and 2. And then 9 and 3. So I'm going to square root of x. Imagine it's transferred to it's not. Now we're replacing y with 1/2 y. We're going to get 1/2 y equals square root of x. So I have a vertical stretch by a factor of what? Get the y, so I flip it by a factor of 2. From the x-axis. I know it didn't ask us for this, but it doesn't hurt to write. So my coordinates were x, y. They're going to become x and 2y. So every x is going to stay the same. Every y is going to be multiplied by 2. So x is 0. 0 times 2 is 0. So that's going to stay the same. Then x is 1. And then 1 is y. So 1 times 2 is 2. So we need 1 and 2. Then 2 and 4. 2 and 4 is going to become 2 and 4 times 2. which is 2 and 8. 4 and 2, not 2 and 4, I'm a little backwards. 4 and 2 is going to become, sorry, 4 and 2 times 2, which is 4, 4. And then this becomes 9 and 6. So we're going to start what you did last year. Horizontal, like I said, very minuscule, right? Not like in big detail and all. So we're going to have horizontal stretches. Now some people will say, well, can I move it away from the X? You can never move it away from the X. So because you can never move it away from the X, it always flips. Always. So that's why with the Y, I always move it to the Y, so it always flips as well. So I'm always just flipping them. Because if not, you're flipping the X for sure. And if you don't move it with the Y, then you're keeping it. If you move it with the Y, you're flipping it. Then people are like, oh gosh. So I would just move it with the variable and flip. Move it with the variable and flip. Whereas X is always with the variable. So here, if we have it beside the X, multiply horizontal stretches out in the form Y equals F of X, where B stretches the graph by a factor of 1 over B. And you always flip it. It's with the X, just like when I was doing it, it was with Y, right? Same thing. So your point XY becomes X over BY, or that's confusing to you, 1 over BX. You just times the X by 1 over B. You're timing it by the horizontal stretch. Points on the y-axis are invariant, which makes sense because on the y-axis your x's are 0. 0 times x, anything is still 0. And if B has a negative sign, it's a reflection of the y-axis. It's not a horizontal stretch by a factor of negative whatever, right? Our horizontal vertical stretches are never negative. So to describe the transformations that happen here, it's beside the S. With the S, it's a horizontal stretch. By a factor of what? 5 over 1 now, so it would be 1 over 5. Do you see why I move it with the Y as well then? So it's always just flip, always flip, always flip. If you move away from the Y, you keep it, and then it's like, oh, what do I do? So if it's with the variable, you flip it. Just like you flip this side, it's translation, right? So it's going to be horizontal stretch by factor of 1/5 about the what axis? The Y. Just like it's a reflection in the Y when you have a negative inside of the X, it's a stretch about the Y when you have a stretch. If you want to do mapping just to show it, it would be XY would become 1/5 X on the Y. So your stretches multiply. The horizontal stretch multiply your X side, because the vertical stretch multiply your Y side. Because with the X is X. Yeah. Okay, we have this graph. Given the graph of y equals f of x, sketch the graph of y equals f of 2x. So remember, nothing. We're changing points. So it's going to be xy is going to become what? Something x comma y. You got a horizontal stretch by a factor of 2 or a half. 2 or a half. I'd say 90% of you actually know the answer. A half. So this is a horizontal stretch by a factor of 1/2 about the y-axis. Which means I'm going to get a half x. So all of these points, the y's are going to stay the same, and the x's are going to be half, right? Which means divided by 2. So all my y's are going to stay the same, 0, 2, 5, 0. And all of my x's are going to be divided by 2, or multiplied by a half. So -2 multiplied by a half is -1. -1 multiplied by a half is -1/2. 0 multiplied by a half is 0. And then 4 multiplied by a half is 2. So my new points are at -1 and 0. negative a half and 2. It's going to stay the same because I have to 0 on the y. And then 2, 0. When you're done, try it down.
I good. I haven't been actually recording my voice. So.
So, this one you're going to have 0, 0, 1, 1, maybe 1, maybe 1, 1, 2, 4, maybe 2, 4. And then you replace x with 2x. So you're going to get y equals, and you're replacing x with 2x. Let x is being replaced with 2x. So we're not going to get 2x squared like that. We're going to get 2x squared because you're replacing the x. You're replacing this x. You're taking that x, you're throwing it out, and you're replacing it with 2x. So fucking, number, like this. Right. So we have a horizontal structure factor of a half. So all my x's are being half. And then this would be at negative 1. Yeah, half. This is at 2, so it's going to be at 1. The 2 is going to be at 1. So you have x, y, you're going to end up getting 1 half x comma y. So for example, when I put that negative 1 and 1, it's going to be negative a half times negative 1 and 1. So it's going to be negative a half and 1. So basically every x is being half and all the y's are changing. I want you guys to flip to example 6 and example 7. All right. We have more. So what I told you to do is always do everything that's not with the x over to with the y, right? So the only thing on this one that's with the x right now is the x squared. The first thing I'm going to do is subtract that 3 over. So I'm going to get y minus 3 equals negative 2x squared. Then I'm just going to divide by negative 2. Dividing by negative 2, let's put this in brackets. Dividing by negative 2 is like dividing this whole thing by negative 2, right? Or multiplying the whole thing by negative a half. So I could divide this whole side by negative 2, or I could just multiply it by negative a half. I'm going to multiply it by negative a half, because that's my stretch very close. So ultimately, my equation is negative a half, y minus 3 equals x squared. So, I have to go stretch, reflect, translate, SRT, right? These are all with the y's. So it's going to be a vertical stretch, it's going to be a vertical translation, and it's going to be a reflection about the x-axis. So, I have a vertical stretch by a factor of 2. Then we'll flip it. About the x-axis. not negative 2. And if you're someone who wants to write negative, stop yourself. So we have to do stretches, then we have to do reflections. So this would be our S, and we have to do an R, and everything. I do have a reflection because I have a negative here. So I don't see the negative. The negative doesn't stretch it any differently, it makes a reflection. This is a reflection in the x-axis. And then T, SOT. Now I have a vertical translation, 3, what? It's 3 up. Because it's with the Y, I do the opposite, right? So here I stretch for 2. Here I go up instead of down, right? Let's change. Oh, I also do it with the Y. B, you will get a question like this on your test. You will get a question like this on your diploma. I would be very shocked if they don't. At least incorporate this somewhere. A lot of people will tell me, okay, reflection in the Y, horizontal stretch back up to the half. That would be all correct. And then they'll tell me horizontal translation 4 left, and you are wrong. And that answer is on your diploma. And you're like, how are you wrong? What you told me? What I told you was, if you have it in the form y equals x plus 3, that would be 3 left, let's say, right? I told you this form is what you have to have. But you didn't notice is what's in front of my x? A 1. What's in front of my x right now? A negative 2. You can't tell me a horizontal translation if that is not a 1 in front of the x. So you have to remember to pull the negative 2, GCF it out of those two terms. And everyone forgets. Okay, until it's peaked into all. And if you get it wrong like 4 times, so people start remembering. Okay, so let's make it on like 9 and remember it now. Okay. We have to take this negative 2 out of both terms. So we're going to get y equals negative 2 bracket. Negative 2x divided by negative 2 is x. 4 divided by negative 2, that's what you're doing when you have GCF. What's 4 divided by negative 2? Negative 2. So this actually is not a horizontal translation 4 left. It's actually a horizontal translation 2 right. You have to remember to take that value up. You can't tell me horizontal translation unless there's a 1 in front of that x. That's why the vertical translation works here, because there's a 1 in front, because I moved the 3 over first, and then I only put in that stretch, right? So I still do have to bracket. But everyone forgets to pull this 2 up. You need to have like another bracket in here if you don't stretch. The value in front of your x has to be a 1 in front. So what do I have here? X. I have a horizontal stretch by a factor of 1/2, because it always flips with the x, about the y-axis. I have a reflection in the y-axis because reflection in the y-axis, reflection above the y-axis is at a negative part. And I have a horizontal translation to right. And your homework is on the same as your reflection homework, same page, but stretch. So it's page 28 on. Numbers 5AB. And these ones aren't as bad because they kind of are just stretches. This is leading you into tomorrow when you combine them all. You combine translation, stretches, reflections, they're all combined. You can have every single one of them. Okay? So this homework isn't as bad, it's considerably easier. No. So C3 has a table, and I made you do the first part and the second part of the table, and you can just do the third and fourth line. Let's do the third and fourth line of the table. Make sure you can do this stuff. Make sure you have actually completed all of your homework by tomorrow, or I promise when you put them all together, your head will be spinning. And I know what your head's spinning.